Eightfold Way Physics. In physics, the Eightfold Way is an organizational scheme for a class of subatomic particles known as hadrons that led to the development of the quark model. American physicist Murray Gell-Mann and Israeli physicist Yuval Ne'eman both proposed the idea in 1961. The name comes from Gell-Mann's 1961 paper and is an allusion to the Noble Eightfold Path of Buddhism. Background: by 1947, physicists believed that they had a good understanding of what the smallest bits of matter were. There were electrons, protons, neutrons, and photons, the components that make up the vast part of everyday experience, such as atoms and light, along with a handful of unstable, i.e., they undergo radioactive decay, exotic particles needed to explain cosmic rays observations, such as pions, muons, and hypothesized neutrino. In addition, the discovery of the positron suggested there could be antiparticles for each of them. It was known a strong interaction must exist to overcome electrostatic repulsion in atomic nuclei. Not all particles are influenced by this strong force, but those that are dubbed hadrons, which are now further classified as Meson's middle mass and Baryon's heavy weight. But the discovery of the neutral kaon in late 1947 and the subsequent discovery of a positively charged kaon in 1949 extended the Meson family in an unexpected way, and in 1950 the law. These particles decay much slower than they are produced, a hint that there are two different physical processes involved as suggested by Abraham Pais in 1952. Then, in 1953, M. Gell-Mann and a Japanese pair, Tadao Nakano and Kazuhiko Nishijima, independently suggested a new conserved value now known as strangeness during their attempts to understand the growing collection of known particles. The trend of discovering new mesons and baryons would continue through the 1950s as the number of known elementary particles ballooned. Physicists were interested in understanding hadron-hadron interactions via the strong interaction. The concept of isospin, introduced in 1932 by Werner Heisenberg shortly after the discovery of the neutron, was used to group some hadrons together into multiplets, but no successful scientific theory as yet covered the hadrons as a whole. This was the beginning of a chaotic period in particle physics that has become known as the particle zoo era. The Eightfold Way ended up being an important big step towards the quark model's solution. Organization. Group representation theory is the mathematical underpinning behind the Eightfold Way, but this rather technical mathematics is not needed to understand how it helps organize particles. Particles are sorted into groups as mesons or baryons. Within each group, they are further separated by their spin-angular momentum. Symmetrical patterns appear when these groups of particles have their strangeness plotted against their electric charge. This is the most common way to make these plots today, but originally physicists used an equivalent pair of properties called hypercharge and isotopic spin, the latter of which is now known as isospin. The symmetry in these patterns is a hint of the underlying symmetry of the strong interaction between the particles themselves. In the plots below, points representing particles that lie along the same horizontal line share the same strangeness, as while those on the same left-leaning diagonals share the same electric charge, Q, given as multiples of the elementary charge. Mesons. In the original Eightfold Way, the mesons were organized into octets and singlets. This is one of the finer points of differences between the Eightfold Way and the quark model it inspired, which suggests the mesons should be grouped into nonets groups of 9. Meson octet. The Eightfold Way organizes 8 of the lowest spin 0 mesons into an octet. They are K0, K plus, K and K0 kaons, P plus P0, and P pions. Diametrically opposite particles in the diagram are antiparticles of one another, while particles in the center are their own antiparticle. Meson singlet. The chargeless, strangeless eta-prime meson was originally classified by itself as a singlet. Under the quark model later developed, it is better viewed as part of a meson nonet, as previously mentioned. Baryons. Baryon octet. The eightfold way organizes the spin-1/2 baryons into an octet. They consist of neutron n and proton p, s0 and s plus sigma baryons, L0, the strange lambda baryon and the 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 baryon, Ks and K0 Roman 11 baryons, baryon decuplet. The organizational principles of the eightfold way also apply to the spin-3/2 baryons, forming a decuplet. D, D0, D plus, and D plus plus delta baryons, S asterisk, S asterisk 0, and S asterisk plus sigma baryons, Ks asterisk and Ks asterisk 0 Roman 11 baryons. Omega baryon, however, one of the particles of this decuplet, had never been previously observed when the eightfold way was proposed. Gell-Mann called this particle the O and predicted, in 1962, in 1964, a particle closely matching these predictions was discovered by a particle accelerator group at Brookhaven. Gell-Mann received the 1969 Nobel Prize in Physics for his work on the theory of elementary particles. Historical development. Historically, quarks were motivated by an understanding of flavor symmetry. First, it was noticed 1961 that groups of particles were related to each other in a way that matched the representation theory of SO3. From that, it was inferred that there is an approximate symmetry of the universe which is parametrized by the group SO3. Finally, 1964, this led to the discovery of three light quarks up-down and strange interchanged by these SO3 transformations. Modern interpretation. The eightfold way may be understood in modern terms as a consequence of flavor symmetries between various kinds of quarks. Since the strong nuclear force affects quarks the same way regardless of their flavor, replacing one flavor of quark with another in a hadron should not alter its mass very much, provided the respective quark masses are smaller than the strong interaction scale which holds for the three light quarks. Mathematically, this replacement may be described by elements of the SO3 group. The octets and other hadron arrangements are representations of this group. Flavor symmetry. SO3. Connection to representation theory.